Yeah, hi everyone. Let's wait for a few more minutes in case people are still joining and then we can start. Sorry. I see someone has given something in the chat as the exam is approaching. Can you provide a list of sums for practice along with the answers? So, yeah, I have been providing, right, for the last 8 weeks. Many sums are there with the answers and your assignment problems also. So, I saw that you had mailed me also about this, but I saw the mail like just before the class. So, I was not able to find any questions immediately because I had already prepared for today's class. But yeah, let me see. I think what you can do is you can look up online. There are many such resources. I have also linked many lecture notes and other things in my lectures, so you can check those. Those always have the lecture notes that I have you know linked in my classes. They usually have some problems also, so please go through those notes. Like, I have always linked something or the other in all of my slides, so please make use of those links. I think from there you can find some problems. Yeah, so in the lecture notes itself you can find some problems. If not, you can search online and you can find them. So please try that. I would say that first you can also try the assignment and the other questions as well. If I find any other questions, I don't know, like, I will try to make it available, but other than that, I would say that this itself is a good enough thing. So yeah, I did not see your mail until before the class, so I was. Ma'am, can you give the sources online? Yeah, I give the sources in all of my PPTs. So you can check all the PPTs. They will have hyperlinks. If you click or you copy paste those links, you can find the lecture notes that I'm using. So you can do that. Otherwise, you can search for, nuclear astrophysics, very broad subject. You can search online and you will find a lot of problems also. And I have also told you about some textbooks, etc., which should help you about from this perspective. Yeah, okay, cool. So, right. So, yeah, so I understand that your exam is nearing soon. So, this is why we have this session. So, I think people can continue joining, but we will start the session now. Just give me a second. I'll close my door because, again, there's some construction going on. Yeah. Okay. So, right. So, once again, welcome everybody. Welcome to the last class of this course, last problem solving session of this course that we are going to have of nuclear astrophysics. So, this is going to be a revision class where we are just going to quickly look at and try to summarize all the things that we've looked at over the past 8 weeks. And as you know, there have been many such, things that we have looked at, and many such, concepts across few different fields actually, including nuclear physics and astrophysics and their intersection. And as you know, we have been having these weekly sessions where we solve problems, and I have also tried to best of my ability to include some extra material along with your coursework, so that it is not, just a problem solving session, but you also gain something. It's not just a mechanical section, but you also gain some physics insights or some extra things if you're interested in such a thing. So I would say that, whenever you study such a course, try to have a perspective where you don't just study for, an exam, because exam will come and go in 3 hours, right? But what you should try to do is, like, you should try to see it as a perspective of you are enhancing your knowledge. And hopefully, you have enhanced your knowledge over the last 8 weeks on aspects relating to both nuclear physics and astrophysics. So yeah, of course, exams are important to, give us that push to, kind of actually study the material and give us that extra motivation. But also, uh, please don't be too stressed about it. I'm sure you will all do well. Just use the material that you already have on hand. I think that will be adequate. You will can do look at assignments, lecture notes, and also, these extra problem solving sessions, their problems, and I have provided the solutions for all the problems and the concepts behind it. So as I said, like, all the slides and videos are available to you. They have been available to you right from the first week, so make sure you make use of it. And yeah, you can write to me in case you want something specific, like, if in a specific topic, I would say first you try looking back at the resources that I've already provided you in the form of the assignment problems and the lecture notes that I've linked in my slides. If at all you are not able to find problems relating to some specific thing, you can write to me over the next few days. I will also be a little busy, but I will try to respond to the best of my ability. So yeah, you can write to me with some specific question, but please don't ask me to, like, just give you a list of questions, because as I said, and as you will see in this revision session, we have covered a big broad length of topics, right? And every week I have spent time over last 8 weeks to, curate problems for each of them. I mean, curate links for each of them. So first try to look at those links, and then if you feel like you need extra material beyond that, you can write to me. Okay, so this is, as I said, a revision session. So we're going to just look through everything from the beginning, like a very quick session. And if you feel like you need extra attention to any of the particular topics, then I would recommend that again, as the lecture notes and the slides and the videos are available, I'll point you to go and look at those in some more detail. Okay, so with that, let's start the session. So, just to recap, in this course, you have kind of looked at a broad range of topics, and roughly you have looked at astrophysics. It's linked to the theory of nuclear reactions. You have looked at astrophysical sources and how they're relevant with the point of view of nuclear physics. For example, what are the astrophysical sources where nucleosynthesis takes place, how nuclear physics dictates how stars live and die, HR diagrams and all such things, observational astronomy to some extent. And then you have seen how the theory of nuclear reactions can be linked to the astrophysical processes that we do observe. And finally, we have, in the last 2 weeks, particularly looked at experimental nuclear physics and how exactly, these theories are tested and how the quantities that are relevant to us are measured. So, as I said, this course has actually, in the last 8 weeks, you have actually covered a broad range of topics. So you might feel like, I feel like in this course, it has been very well structured in such a way that you get a feel for a broad range of topics. And now it's up to you, as per your interest, as to what kind of topics you find interesting in these particular fields, to pick them up and pursue it further. Because I hope that your journey with nuclear astrophysics and astrophysics or nuclear physics particularly does not stop just with this course, but you will, with this basic knowledge, you can continue on and, maybe explore more about it. So courses like this should be taken in that way. I feel like you should try to take the course and look at the topics, because there's a lot of topics covered. So maybe something might not be covered to the depth you want. So it is kind of like, uh, you want to look at, the yeah, you want to look at some topic that you want to explore it in more detail. Sorry, I saw something in the chat. Can we mail you about problems regarding nuclear astrophysics or astrophysics even after the course finishes? Yeah, sure. So you can always mail me, or my mail is with you. So if you want some general advice about physics, astrophysics, or even how to pursue a PhD or something, you can mail me. I will try to respond as per my availability. And yeah, we just yeah, as don't ask very broad questions, but if you ask me something specific, I will be able to always help you out. Or even if I don't know much about it, I can point you in the right direction. So yeah, feel free to mail me about it after the class also. So right, okay. So as I was saying, in this course, you have seen a broad range of topics, and we can, and this is the picture that I have been showing from the, I guess the first class is this sort of picture, because I feel like this is a very nice, like, condensation of the essence of this class, right? You can see how, the nuclear physics and the atomic physics that we deal with on Earth are very intrinsically linked to astrophysics. And that's how we have to think about it. Each element on the periodic table can be linked to some or the other astrophysical processes. I mean, apart from the man-made ones, but every naturally occurring element can be thought of as the, can be thought of as coming from some astrophysical process or the other. So that's where this whole "we are made of stars" stuff kind of idea comes from. And I hope that now at the end of this course, you have, an appreciation for this picture. You understand these different mechanisms, at least at some preliminary level. And, obviously we cannot be an expert at everything. So again, as I said, this course is kind of like an exposure to you. And I hope that, whatever interesting concepts that you have picked up during this course, you will go ahead and pursue it further in some way or the other. So yeah, I thought that we can very quickly go through what all we have done over the last 8 weeks. So in the first week was essentially an astrophysics kind of, astronomy and astrophysics kind of introduction. And you saw that how astronomy and astrophysics has evolved, how different stars, galaxies, ISM, there are many components in the universe. It's not just the stars and the planets, but there are different kind of objects. And we know that from this picture that, sorry, that the different elements, there are all the different elements are present in various astrophysical centers and astrophysical quantities, from which we can kind of find out an elemental abundance curve. You also saw that there is active nucleosynthesis happening in stars based on certain observations. So what you were seeing was how multi-messenger astronomy is done based on different missions which take place across the electromagnetic spectrum. So, for example, we need all kinds of measurements along the electromagnetic spectrum, but also we need um, observations from neutrinos, and nowadays from gravitational waves as well, because all of this gives us a complete picture. And I showed you how our own sun can be imaged in different wavelengths, and that shows us different aspects of it. Like the corona, the very hot outer layer, may only be imaged in X-rays, whereas some other aspect of the sun may only be imaged at UV rays. So it's important for us to have multi-messenger astronomy. It's basically like giving different viewpoints to this same object, and that helps us to understand a complete picture of it. And of course, if we want to theoretically understand the complete picture of it, the nuclear physics aspect is very important. You also saw that stellar populations exist depending on their metallicity, whether they are high and low. And you also know that the population one stars with high metallicity are younger, because they are the a result of an already evolved population to stars dying and producing elements. So already you can see, even in the way that we talk about stars and their classification, the nuclear physics aspect plays an important role, because we kind of classify stars and stellar systems, and we are able to estimate their ages based on exactly what are the kind of nuclear reactions that have happened in that system. We also saw, as I mentioned in the introduction, the elemental abundance curve. You know that hydrogen and helium were produced during the Big Bang, but the other elements has to be produced through other methods, like fusion processes that happen inside stars, which you also saw. You know that this is a picture that you would have known before your course, which is that iron is the most stable element. And this has important implications for how we understand stellar physics, right? Because an important aspect of stellar physics is understanding how hydrostatic balance is achieved, which is where pressure balances gravity, and that ensures that the star does not collapse in on itself. So, speaking of stellar physics, the second week, one of the very important things that I mean, there was a lot of different concepts that were covered, but one of the most important concepts, according to me, and I think that, you will also find that this is one of the central concepts of stellar physics and astrophysics, is the concept of the HR diagram and stellar evolution. So, as I said, nuclear physics plays an important role in dictating how stars live and die, and how we classify stars, how we understand stellar populations, everything. So that means that, as we understand the evolution of a star from its birth to its so-called death, we have to really understand the nuclear physics. So you saw essentially what is the life cycle of a star, and we also saw that depending on the mass of the star, we actually get different kinds of evolution. So I showed you how low mass and large mass, heavier mass stars, so low mass is like stars like our sun, or close to sun's mass, maybe around 10 solar mass or lower, and larger stars are anything above that. And you see that how their evolutions are completely different because the masses are different. And the reason the mass being different plays an important role in how the evolution is different is because, of course, if the evolution was the same, then sorry, it's because if the mass is different, then the nuclear reactions which are happening in the star are decidedly different. So what happens is, as I said, the central idea of stellar physics is pressure balances gravity, which is given this very fancy name of hydrostatic equilibrium. Well, the way that a star maintains itself and remains stable on the main sequence, as it's called, is through hydrogen core burning, as burning releases energy, and pressure and the inward push of gravity is balanced by that released energy. So here burning, of course, you guys should know by now, refers to nuclear fusion. So hydrogen fuses to helium with release of energy, and we did calculate how much that energy is. It one such reaction releases around 26 mega electron volt of energy. We also, in one of the early classes, compared different stabilization time scales, and we found that it is only the nuclear physics point of view that can explain why the sun has such a long life. If it was just supported by thermal pressure or something, it would not have lasted this long. So yeah, so the point is that if the star once the star runs out of hydrogen burning, that's when the main sequence ends. And of course, because there is no longer any pressure to support the star against gravity, it contracts, and as it contracts, the core heats up, and this leads to if there is enough material, there will be further burning, which is helium burning with shell burning of hydrogen. And we saw that such a sequence of elements can happen depending on the mass of the star. So when the star is less than 8 solar mass or so, then what happens is there is no burning beyond, say, oxygen burning or something like that. And we end up with what is called a white dwarf after a phase of red giant and going through this planetary nebula phase. And if the star is higher than 8 solar mass, it can actually go all the way up to iron, which, as I showed you in the previous slide, we know that iron is the most stable element because the binding energy is highest for iron, the modulus of the binding energy. And if the binding energy has a higher value, I'm saying value as an absolute value, that means that I need to put in more energy in order to break iron apart. So it does not fuse very easily because it is at the most stable state. As I've told you many times over this course, everything in the universe wants to go down to the lowest energy state, and iron is already in a quite a stable configuration. So to break that, we need to put in more energy, and that is why iron fusion does not happen. And once the star fuses all the elements up to iron, it's no longer able to support itself through simple nuclear fusion, and there is a sequence of steps called core collapse, where it completely, the core completely collapses to this degenerate object, and the rest of the outer layers are blown off in this explosion called a supernova. And the result of that is, of course, either a neutron star or a black hole. I've also to some degree told you about white dwarfs, neutron stars, and black holes. Particularly I've told you about white dwarfs and neutron stars because this is very close to me, because my research is centered around these two objects essentially. So here you can see that all the different stages have been put together. You can see how, you know, if the initial mass is greater than 0.08 solar mass, which is the protostar phase, then only it can be called a star. Anything below that is called a brown dwarf. And of course, that is not really a star, it's a failed star because it does not even have enough mass to start hydrogen burning. So you can see that the very reason why we can call something a star, the way that we define its evolution, everything is linked to nuclear physics, right? So that's why nuclear physics is very much, in tandem with astrophysics, and that's why such a course is important. So yeah, so it goes through all the phases, and then, if the mass is less than 8 solar mass, it does not really go into all the multiple shell burnings, but it stops. It can even go up to carbon burning, but that's the maximum of it. It cannot burn oxygen. So beyond that, it forms a neutron star black hole. So these are the stellar deaths, basically. And you also saw about the HR diagram. The HR diagram is basically an observational diagram that is constructed based on the observations of the stars that we see around us. So you can see that the main sequence stars are all on this phase, and you can see how bluer stars are bluer stars are hotter and redder stars are cooler. This you can understand based on the Wien's law, because you know that stars can be approximated to be black bodies, and from this I think we did an exercise where we can very easily estimate what could be the temperature of the sun at the surface based on the fact that we see roughly yellow light that is peaking in its black body spectrum. So because of that, we are very easily able to understand why red stars are low in heat and blue stars are higher. You can see the white dwarfs are lowly luminous objects. You have the giant phases, which is what happens when it's out of the main sequence. And of course, our sun is somewhere here. And you know that there are different classifications for these objects, like the Harvard classification scheme. So this is exactly the system that I was talking about before, the sequence that I was talking about before. So 1 second. Basically, this is all the sequence of nuclear burning that you expect. If the star is heavy enough, it can keep on fusing elements to higher and higher atomic numbers. You go from hydrogen to helium, helium to carbon through triple alpha, carbon to neon, neon to oxygen, and so on until iron. And of course, because of this diagram, iron does not fuse because it does not give us exothermic reaction. And we really need exothermic reaction because the whole reason for nuclear fusion is that we need some release of energy to balance the inward push of gravity. So this is about week 2. In week 3, you started moving more towards the nuclear physics parts of it. So you learned about different reactions and reaction rates and lifetimes, but also, you learned about the Maxwell-Boltzmann distribution. And I remember some of you had written to me about the Maxwell-Boltzmann distribution. So week 3 problem solving session was exactly about the Maxwell-Boltzmann distribution. If any of you have any more doubts about what is the Maxwell-Boltzmann distribution physically represent, or you want to understand it better, I urge you to go and watch the week 3 lecture or see the slides. I have included a lot of information about it. But quite simply, the Maxwell-Boltzmann distribution function is basically a probability, right? So whatever the function f of v, which is the Maxwell-Boltzmann function, it returns to me the probability that a random atom in a gas has a speed which is that V, right? So essentially, Maxwell-Boltzmann's function is a probability distribution function in the sense that it does not make sense to talk about a Maxwell-Boltzmann distribution for one particle, right? This is an inherently statistical property. So you need many, many particles. You need a distribution of atoms like you see in, for example, a gas. And from that, you can see that in an ideal gas, the velocities follow exactly a Maxwell-Boltzmann distribution. So this is basically a probability function. And because we know that all probabilities should sum up to 1, we know that the area under a Maxwell-Boltzmann curve is always 1. Based on this, you can always estimate how a higher temperature Maxwell-Boltzmann curve will look as compared to a lower temperature. You know that, the a more peaked Maxwell-Boltzmann temperature curve like this actually indicates that the temperature is quite low, the mean temperature of the gas, whereas a flattened curve kind of tells you that there is more particles with higher speeds, indicating that the temperature is high. So one thing that you have to get used to in physics and nuclear physics or astrophysics is that temperature, energy, velocity, these are all related to each other. So higher temperature is just a measure of kinetic energy. So when we say temperature and energy, they are kind of related. We also saw how to convert between temperature and energy using the Boltzmann function, the Boltzmann distribution function. And apart from that, you also know that, of course, later you saw that mass and energy are also related. So, sometimes people say mass, but they represent it in mega electron volt. They say temperature, they represent that also in electron volt. Don't get confused. It's always up to some normalization or some constant factor or the other. So yeah, so from the Maxwell-Boltzmann distribution, because it's a probability, I can find out where is the probability maximum. And that tells me what is the most probable speed, right? Similarly, I can find the mean speed, I can find the root mean squared speed, and these all have interesting implications. We have also found out how to calculate these things. So again, like I think the week 3 problem solving lecture was completely about the Maxwell-Boltzmann function. So please take a look there if you have some conceptual understanding. But in the essence of it, it's basically just a probability function, probability that a particular particle at random from a gas has a particular speed. And that tells me about the Maxwell-Boltzmann function. Okay, so the week 4 lecture is probably the most mathematically intense of all of them. I mean, the week 4 problem solving session, especially because you learned about this gamma factor, gamma peak, and astrophysical S factor. And there came a lot of formulate together in that sense. But if you again, I would say that if you go back and watch the week 4 lecture, you can see that actually all those formulae which are given to you, they are not all disjoint, right? They all follow some sort of sequence because they are all kind of related to each other. They are all related to finding the cross section, and the cross section is an important idea because that kind of tells you about how likely it is a reaction happens or it doesn't happen. So we also saw about non-resonant and resonant reactions and all that stuff. So again, like you can go and watch the lecture also, because I tell you how the sequence of reaction equations are all related to each other. So basically we start with the reaction rate, and in order to calculate reaction rate, we need cross section. But in order to cross section, we need the probability. And in order to calculate the probability, we need to understand quantum tunneling. So one thing that's useful in physics is to kind of have a handle on why we are doing this, right? Why are we doing such a big calculation? It's because there are these quantity. So keep in mind what is the quantity you want to calculate and what are the different things I need for that. So you will find that everything is interconnected in some way. So you don't have to study, cross section formula separately, time, what is it called, lifetimes formula separately. That does not make sense. So rather you have to understand that these two things are kind of related to each other. The cross section gives you the rate of reaction, and the rate of reaction is kind of like the inverse time, right? Because that's how you think about it. So try to relate the things that you learn. And for example, the Maxwell-Boltzmann distribution that we just talked about is very important because it tells you how molecules are distributed in a gas, and eventually, it might be that the most energetic particles will react and maybe they won't, the others won't. So we have to know about these things properly in order to uh, yeah, in order to uh, perform their calculations. So if we now go, so this was like the picture of, I put 3 pictures from the lecture, and all 3 of them, give us the complete story of what's happening. So these 2 pictures are together giving us a story of this picture. So first of all, what we saw is that when 2 nuclei interact, then there is a very big problem, because these are both like charges, right? They are both positively charged elements, and we are making them interact. But we know that like charges have a Coulomb repulsion between them. So we always see that there is a repulsive barrier between the atoms. So we need to give a lot of energy in order to overcome this barrier. This is essentially the same as when you take like poles, because electric force and magnetic force are just 2 sides of the same coin. But if you take 2 like poles of a magnet and you put put them together, you know that they give a sort of repulsion, and we need to put a lot of effort to even bring them together. And that is exactly what happens in the case of the nuclei. But unlike magnets, what happens is, magnets, we will never be able to stick them together. But unlike that, for nuclei, below a certain radius, another force starts dominating, which is called the strong nuclear force. So we already discussed how there are four fundamental forces in the universe. Gravity is the weakest and the strong force is the strongest, because how are atoms held together? How is a nucleus held together when all the protons are repelling each other and want to blow themselves apart from Coulomb repulsion? The answer is that there is a stronger nuclear force which is holding them together. And you can see that below a certain threshold we get an attractive nuclear potential. And of course, we already have calculated what is the Coulomb barrier for, say, a proton proton interaction, and from that we can get the energy that is required to overcome that barrier. And we found that, because as I said, energy can always be thought of in terms of temperature, we saw that we really need a very high temperature in order to overcome that barrier, which is not really happening in our sun. So then the question becomes, how are reactions happening in our sun in the first place? So the point is that, because there is our old friend quantum mechanics helps us out, and this is exactly where quantum tunneling comes into the picture. So as I think, through this course I've tried to give you a little bit of a flavor of quantum mechanics if you don't know it already. But basically, in simple terms, quantum mechanics is the weird kind of physics that governs the behavior of particles at very small scales. So small scales means on the scale of nucleus, on the scale of electron. And the reason why at small scales it's important is because everything in the universe, including you and me, have a dual nature, which is that we have both a particle nature, or a, in my case, we are made of many particles. But yeah, our atoms have particle natures, but they also have wave natures. And the point is that when you go to very big scales, that wave nature kind of gets washed out. The wavelength is so small that you can't even notice it. But when you start off with something that's already very small, both in size, in mass, then what happens is that the wave nature is important itself enough that it can influence how the particle behaves. And that makes quantum mechanics weird. So quantum mechanics is not weird in the way that its physics is particularly different. It's just the physics of waves. Why it's weird is because we don't expect particles to have a dual nature, because we live in the size range where the wave nature doesn't matter. So our daily experience with life is that there is no such wave nature that we can just get by assuming everything is nice and Newtonian, everything has just a particle nature. That's why we find it weird and unintuitive. But from a physics point of view, quantum mechanics is actually the more general theory, and Newtonian mechanics is simply an approximation of it. So the point is that quantum mechanics really helps us out here, because without quantum mechanics, our sun could have never kept stable. Because as I said, for a star to remain stable, you need some sort of force to balance it against gravity, which is provided by the nuclear burning. And the proton proton Coulomb barrier is high enough that without the phenomenon called quantum tunneling, the the particles would not have bonded together to produce an alpha particle or a helium particle in the first place. So basically, the principle is what is shown here, which is that a wave function, which is simply how we describe particles in quantum mechanics. As I said, they have wave and particle nature. You can see that when it hits a barrier, a small part of it, very small part of it, may be transmitted. And it turns out that the probability of some particles transmitting through the barrier is very small, but it is high enough that it is able to sustain the energy of the sun. And we also calculated how many particles classically penetrate the barrier. So that, of course, comes from, again, as I said, everything is related. So you know that the Maxwell Boltzmann distribution tells us that if I take a gas in general, and if it's a gas of temperature, say ideal gas of temperature T, that does not mean that every single particle has temperature T, right? It might mean that many of them, the most probable temperature might be T, which means that majority of them, maybe 70-80% of them have T. But if I take a particle at random, there are a very small probability that it will have either a very high energy or it will have a very low energy, right? So this is what I mean by the distribution function. So just because a gas has temperature T, that does not mean that every single particle has a temperature T. That's not how it works. That's what the Maxwell distribution function tells us. So of course, there is a very small probability that some particles are very energetic, some protons are energetic enough that they overcome the Coulomb barrier just by being energetic enough. But we also calculated the probability of that, and when we compare these two probabilities, we find that quantum tunneling, though as unlikely as it is orders of magnitude, I think even 200 orders of magnitude more likely to happen when compared to the simple classical um, perspective. So this is what I mean by, astrophysics is an extremely interdisciplinary subject, right? In order to be an astrophysicist, you need to know about basically every branch of physics. So you have already seen firsthand how nuclear physics is kind of involved at every level when it comes to an astrophysical thing. But also, you need to have good knowledge of quantum mechanics, of statistical mechanics, of special relativity. So that's why, it's always good to think of these things as operating together rather than putting them in different boxes. And real research is always interdisciplinary, where you have to take insights from different parts of science to put them together. So the gamma peak was kind of the important topic that we covered this week. And the gamma peak is essentially the optimal region where the reactions take place, or the optimal region. When I say optimal region, I mean in terms of energy, and it's kind of summed up in this picture here, but essentially yeah, so essentially it is the understanding of these two pictures, right? So we know that particles are distributed according to their temperatures, and we also know that tunneling happens when particles are at, you know, uh, tunneling is more possible when particles are at high energy, obviously, because it is more energetic. The tunneling probability is directly related to the energy. So more energetic particles can tunnel more efficiently. But at the same time, the Maxwell-Boltzmann distribution tells us that very high energy particles are usually on the tail end of the spectrum, which means that they may be low in probability as well, right? So there are less number of particles. So the gamma peak tells us that window where the tunneling probability is not too low, but there are enough particles at the same time. So these two things where they intersect, that tells us the gamma peak. So you can see here that there is a Maxwell-Boltzmann distribution. For example, in this region, we have a lot of particles, but of course the tunneling probability is essentially zero. So we don't have any reactions happening there. Whereas here you can see that we have very good tunneling probability, but the number of particles is essentially zero, so it doesn't happen. So the gamma peak is neither of these two extremes. It lies exactly in the middle of these two extremes, so that this is the place where the particles can actually take place in the reactions. And we have seen exactly how to calculate this energy of this peak, the width of this peak, and because and why do we need the energy and the width of the peak? Because that is extremely related to the cross section and the reaction rate by extension. So we saw that, cross section, just calculating the cross section might be problematic, because cross section has a lot of dependence on Coulomb repulsion. It has, discontinuity and so on. So when we factor out those things, then we can find out something called the astrophysical S factor, which is another way of just recasting the same information but in a smoother function, right? So we found out how to exactly calculate these things and what is the width of this peak. We found out that if the S factor is very much dependent on certain energies, that indicates that we have a resonant reaction, because that means that the cross section is a very, strict function of the energy, where it is extremely high for certain energies and lower for others. So yeah, so when I keep talking about cross section, but the point is, what is a cross section anyway? So there was this, when I was making these slides, I found this very nice question on Stack Exchange, where someone had asked, what is cross section and why should I care about it anyway? Which is maybe something that you guys have also thought about during the duration of this course. But this person has given a very nice answer, depending by talking about, shooting bullets at a swarm of bees. I encourage you guys to read it. But essentially, yeah, this is the essence of cross section. How far will my bullet go inside the swarm before hitting a bee? And that's kind of how we think about nuclear cross section, right? So you cross section, microscopic cross section, as we saw, is measured in units of area. It's usually called a barn, which is a very microscopic area. And we kind of, we understand that a higher cross section means the reaction has more likely to proceed, because we have a bigger area essentially. So you can think of it as, however you want. You can think of it as putting bullets into a pile of bees. I also showed you this picture in one of our lectures, which is throw aiming guns as at a target or something. But remember that all these sort of analogies only go so far. So as this picture indicates, you know nuclear cross section in the terms of target and bullet is not really correct, in the sense that nuclei are inherently quantum objects. So there's a lot of quantum mechanics involved. You can see that depending on the velocity of the object, the target can get smaller, which is not something that we sorry, yeah, target can change its size, which is not something we really encounter when we look at uh, regular bullets, right? We don't expect the bullet is fired at a higher speed, the target can change size. But because nuclear quantum mechanics speed, this cross section does not depend just on area. It depends also on certain things like the energy of the particle and so on. And of course, there are different kinds of cross sections involved. There is an absorption cross section, fission cross section, scattering cross section, because nuclei interact with each other in different ways, whereas a bullet and a target only really interact in one way. So, whenever you use analogies in physics, you should also know the limits of how far can that analogy be taken. So yeah, this is about cross section. And as I said about this gamma peak and all this, I have already discussed very much in detail in the week 4 class. So if any of you find it a little difficult to follow, I encourage you to go and watch that video and also the lectures, because I think the problems of that week are also like completely connected to each other. So I think if you do that sequence of problems once, you will have an idea about why this matters and how you can connect these quantities to each other. The big picture is that we want to calculate a reaction rate. Reaction rate is dependent on cross section, and as I showed you, cross section depends on various factors, which is depending on both this Coulomb barrier and, more importantly, this quantum tunneling, which comes in because the Coulomb barrier is a little too high. So yeah, please go back and read it. And I thought that today I can just talk about the resonant reactions, which may not be have been covered in the problem solving class. So essentially, this is the general form of a cross section, and you can see that it depends on the energy. So as I said, a bullet that is traveling more fast may have a higher cross sectional area, or vice versa. Here you can see that it seems that the bullet has a resonance at 700 because the target is biggest there, whereas it's smaller for the other two. So you can kind of think of it as 700 is your resonant energy, as you have seen in some of the nuclear reactions. So yeah, so you see that sigma depends on a lot of things. So this is your de Broglie wavelength, your penetration factor, which is basically your quantum tunneling. Again, we have already covered this, and this is the nuclear structure. And again, these are covered in this lecture notes. Please go through that if you have time. And I told you already what are resonant and non-resonant reactions. So you can see that when if we consider S, and S, as I said, is the astrophysical S factor, it is directly related to the sigma. So if S is like a constant, that tells you that it is really not depending on any one energy or the other. So in that sense, it is completely non-resonant reaction, like direct capture, for example, which does not depend on the energy. If it is yeah, this can also be a category of this, where there is a broad resonance and something is happening at the lower end of it, which means that it is not really depending on the resonant peak. Whereas if SOV is highly variable, that means it's very strongly related to the energy, and there are certain narrow resonances within the gamma window which are possible. So within this, so the gamma peak is not really depending on whether it's a resonant reaction or non-resonant reaction, right? It just tells me that this is the energy window which is favorable for reactions, and then the sigma factor can be, within that peak itself, the sigma factor can be particularly high for certain reaction, certain energies within that peak itself. So I think we have done such a problem in one of the problem sessions. I don't remember which week it was, where there was a resonant reaction. We calculated the gamma peak, and then we found out which of the resonances fall within the gamma peak, so that we can link these two concepts. So yeah, please make sure that you don't get confused between gamma peak and resonance. They are two kind of different things. Gamma peak tells us the energy window where the reaction can take place, and resonance tells us that, where it is the most sensitive. So if there is a resonance peak within the gamma window, that is where obviously the most reactions will take place. So the resonance energy, for example, for a reaction may not is not depending on it's not particularly depending on its temperature, right? Whereas the gamma peak can shift depending on temperature. So it might be that at a higher temperature, certain other resonant peaks are more active, whereas at lower temperature, some other resonant peak may be more active. And this is how you have to think about it. So yeah, so this is basically, if SOV is constant, then that means that there is a large number of resonances in the gamma window. So again, this is all covered in this lecture. I mean, this is more of a PPT. You can go through it. It has covered all of the things that we need. And I think you have already covered this in your class. So I'm not, I have not put the derivations here. I didn't put any derivations here because this is kind of a recap class. You have already seen all the derivations through your lectures and maybe to some extent in the problem solving classes as well. So you saw that the cross section due to a single resonance, you can find it during using this Bright-Wigner formula. So here this is your sort of your quantum mechanical area. This is the spin factor, and here is the dependence on the resonance width and the energy. So you know that when the width is very small when compared to the energy, that is what is called a narrow resonance. And narrow resonance has its own kind of dependence for the cross section, and you can do various approximations that, for example, the Maxwell-Boltzmann distribution is constant over the resonance, so the probability of particles is basically the same. All widths are constant, and lambda, the de Broglie wavelength, the wave nature of the atom, is constant. And when you make all of these assumptions into this general rate formula, then what you see is, and this is of course the general sort of thing for. Yeah, so finding cross-section of resonant reaction is the Bright-Wigner formula. This tells you the contribution due to a single resonance, right? Whereas if it is a single, if it is a narrow resonance, then it becomes a little more specialized in the sense that, so resonance does not have to immediately mean a narrow resonance. You can also have, a resonance over a large area, right? Whereas if the width of the resonance, if it covers such a contribution, then the resonance energy must be is very narrow. That means that, if you are only if you're very much close to that resonant energy, the cross section is very high, otherwise it's not. So for the narrow resonance, because it's over a small what can I say, width in the phase space of the energy, you can assume that all these quantities are constant over it. And if you put those assumptions into the Bright-Wigner formula, so again, I'm saying Bright-Wigner is for a general resonant thing, and that's why you see gamma 1, gamma 2, etc. are there in the fully thing. But if we then assume that gamma is very narrow, then we can make further assumptions, and then we get the form of the resonance that maybe you have seen in the class involving this gamma, omega gamma, which is the resonance strength. So you can see that for a narrow resonance, we can get a cross-sectional area. Here it's, this is the reaction rate. You can see the reaction rate. It's written in slightly different terms than in the class, but the essence is the same. So there is an omega gamma dependence when we compare with the this case where it's just omega, instead of writing all this down, because of this simplifying assumption, we can absorb it all into this omega gamma factor, right? And we can further, make some assumption about gamma 2 being small, then it becomes even more simpler. So this, I think, you have derived in the class. So Bright-Wigner formulas for general resonant reactions, but for narrow resonances, you can finally see that the dependence fully comes on the resonance strength, which is represented by this omega gamma factor. So the thing is that, yeah, so this is about the other things, which is what I just now said, which is that if we now have a resonance which is in the gamma window or the gamma peak, then we see that the reaction rate is mainly determined by that particular resonance. And as I said, a reaction may have different resonant energies, and the gamma window that it falls into depends on what temperature the reaction is happening at, right? So the gamma window may be around a certain reaction at some particular point of time of temperature, but if it is at a higher temperature, it may be that some other resonance energy falls into the gamma window. So I think I'm just checking if there are any other questions. I don't think so. So yeah, so the other thing is that, if because of the density increases with energy, so higher temperature rates are dominated by resonance and lower temperature rates are usually dominated by direct reactions. And you can see that the reaction rate is extremely sensitive to the resonance energy. And this is all for what we need. So this is about resonance. And so essentially, to sum up these 2 weeks, what these 3 weeks lectures, what you saw was essentially week 3, week 4, and week 5 are kind of all related to each other. So week 1 and 2 were about kind of the astrophysical aspects and the life cycles of stars, and where nucleosynthesis plays a role in astrophysics. When it came to week 3 and week 4, what you really saw was how to describe these reactions in the first place. So there are different categories of reactions. There are reaction rates, and these reaction rates are dependent on cross sections, and we need to find these cross sections in order to um, calculate the reaction rate. So, finding cross section is not as straightforward as finding the area of the target, because as you can see, the area of the target itself depends on the energy. So classically, the cross section would just be the area of the target, right? Because that's what happens when I fire a bullet at a target. But when I fire a nucleus at another, then there is an energy dependence. Sigma depends on E, and that's why I have to go through a lot of painful steps to find out what exactly is that exact dependence, so that I can integrate it out and find the exact reaction rate. And that's where the gamma peak plays a role, because it tells you that for that particular distribution of gas at a particular temperature, where is the maximum reactions can take place, right? So the cross section tells you how likely is the reaction happening, and gamma peak also gives you that information, but from a different perspective. So this is about these 2 weeks. And week 5, again, you saw about how nuclear burning actually happens in the star. So how to apply the concepts of week 3 and week 4 back to week 1 and week 2, which is stars, right? We also saw how to describe nuclei in terms of the shell model and the liquid drop model. So again, this, as I told you, at some point, describing atoms is kind of easy, because we have a central object which is kind of pulling everything around it. So you can think of it as, the it's like our solar system, right? To find the dynamics of the solar system, we only really need to care about the sun and the planet. Of course, the planet like Mars and Earth, they exert some gravitational force on each other, but compared to that gravitational force, the sun's gravitational force is much higher. So we can kind of ignore all those intermediate interactions, and we can focus on the center of mass of the system, which is the sun. Similarly, in an atomic system, it is a nucleus which kind of controls all the dynamics, right? Whereas when we go inside sorry, in an atom, it is the nucleus that controls all the dynamics. Whereas when we go inside a nucleus itself, there is no such localized center of mass. So then it becomes a challenge as to how exactly to describe this. And also, just to clarify, I'm not saying atoms and planetary systems are equivalent. I'm saying that to describe the dynamics, we can focus on one of the quantities in the system. And of course, atoms are different. Planetary models don't apply to atoms. Famously, Rutherford's planetary model of the atom is a disaster. But the point is that, we can focus on the nucleus or we can focus on the sun. But in a nucleus, that is not possible. What will you focus on? And you have to kind of construct average potential which is generated by all the nucleons around it, and that is what the shell model exactly is. So as I said, we first looked at the PP and CNO scales. So one second. So these are the PP and the CNO cycles are essentially hydrogen burning cycles which happen. So they are, of course, these reactions are depending on temperature. So you know that there are kind of three PP chains which are possible. Here I've only shown one of them. And at any point that this is the most dominant chain, which is PP1, but there is also PP2 and PP3, which happens around, if I remember correctly, in some lower like 30% of the time or something like that. So you can see how, the weak interaction phase between hydrogen protons, kind of interacting, that is the one that takes the longest time. And after that, of course, everything takes place pretty quickly. So we at the end, we end up that four hydrogen atoms have to fuse to one helium. And that is what tells us that, how the proton chain happens. And here, how much energy is released. You can calculate it using Einstein's famous E is equal to mc squared formula. And you find that with each of these interactions, 26 mega electron volt is released. The CNO cycle is another way in which hydrogen is fused to helium. So again, even though it's called CNO, it is about hydrogen fusing only, because C, N, and O are catalysts in this reaction, in the sense that they take place in the reaction, but they are regenerated at the end of the cycle. You can see that clearly from this image. You see that hydrogen and carbon interact with the release of a gamma particle into nitrogen, which then, undergoes beta decay to carbon 13, which then interacts with a proton to form nitrogen 14. Again, there is, another proton interaction. Then there's one more beta decay. And then you can see that at the end, we, when the nitrogen and hydrogen interact once more to form helium, we regenerate back the carbon. So we get back what we started with. So CNO take place in the reaction, but they are kind of, they get regenerated. They are not used up in the reaction. In that sense, CNO are not the products or the reactants. If you write down all the reactions and you sum them together, you'll see that we get exactly the same reaction in both the cases, that hydrogen fusion is leading to a helium particle. I also showed you how PP and CNO have different temperature dependencies. And because more massive stars are more hot in their core, you see that beyond a point, the CNO cycle is really dominant. And we see that, we expect that in high mass stars, it is a CNO cycle which actually dominates when compared to the PP cycle. And we can see how that is changing its lifetime and so on. Okay. So this is about the PP and CNO cycle. We also, as I said, saw about how to describe nuclei. So again, as I said, um, just before, describing nucleus is not as straightforward as describing a. Is there a question? Yeah, I don't see any other question, so I will just. Yeah, sorry. I thought there's some chat, but there's not. Okay. So as I said, describing a nucleus is not as straightforward as describing an atom, because of these things. So there have been two main approaches. This is the liquid drop model, and we have already seen how this comes about. You kind of imagine the nucleus to be like a drop of water, and then you have to kind of correct for all those terms. So you have the volume term, which tells you that, the bigger a nucleus is, the more energy it has. And of course, you know that the elements at the surface have less energy, just like how you expect for a negative contribution to energy, I should say. Just like how you expect for a surface tension kind of thing in water, you know that the molecules which are inside, or not molecules, I should say nucleons. Nucleons which are inside the nucleus, they might have interactions with all their neighbors, whereas the nucleons which are present at the surface of the nucleus, they have, one interaction less because they cannot reach out outside the nucleus, right? So that's why the surface term contributes negatively to the energy. The asymmetry term is basically a reflection of the fact that, nuclei which have protons and neutrons which are equal are particularly stable, especially in the low atomic number regime. And this we kind of looked at in detail in one of the later one, either week 5 or week 6's lecture. The Coulomb term tells us that the energy is further, has a negative contribution from the fact that there is still Coulomb repulsion. So even though there is strong forces holding everything together and dominates the Coulomb term, the Coulomb repulsion still plays a role. And finally, we have the pairing term, which represents how even nuclei are most stable when compared to odd nuclei. And like this is called a semi-empirical model because it is kind of dictated by both, of course there's a theoretical model, but it is also dictated by this sort of experiments, right? Because all these sort of terms, the coefficients that you see here are fixed from experiments. That's why it's called a semi-empirical model. So there are some, this explains a lot of things very well, but there are still some things that are not explained. So even though we understand why the surface term and Coulomb term comes, it's not immediately clear why even nuclei should be stable as opposed to odd nuclei, right? So that's why people move to the shell model. So the reason for people moving to shell model itself is this kind of pairing terms existence. People notice that even nuclei, and particularly certain numbers of even nuclei, are very stable when we compare to other numbers. So that kind of tells us that there might be an octet kind of situation here. Like how you know that, for example, the reason that noble gases don't interact at all is because their shell configuration is in such a way that they have fully filled shells. So similarly, was there a reason that these particles are incredibly stable? Is it because their shells are filled in such a way? Interaction with the nucleus, but in nuclear shell model, what we have to do is we have to pick up any one nucleus and we have to consider it to be moving in a time averaged potential that is generated by all the other nuclei. And this is a kind of a deeply quantum mechanical effect, and we describe it using various quantum mechanical potentials with well-known solutions, for example the finite well and the square well, and also at first approximation the harmonic oscillator. So this naturally, because these are quantum mechanical potential, these naturally lend themselves to energy levels. And what we see is because of the fermionic nature of nucleons, as I have described during the class many times, fermions are particles which really don't like to hang out together. They have this Pauli exclusion principle, which means that if you put too many fermions together, they will not, you cannot put too many fermions together. So because of that, because of those two effects, like the quantum mechanics of fermions, we see that we naturally get energy levels which get filled, right? And we see that whenever an energy level gets filled, that's when we kind of get a stable nucleus. And always we know that because a nucleus has a spin of half, both the proton and the neutron, both the nucleons have spin half, you can kind of consider two particles to occupy every particular energy level. And that's orbital, if you want to think of it like that. And that's how we get the magic numbers. So you know that we already have this sequence of states, which is 1s1, 1s half, 1p3 by 2, and that comes from angular momentum addition as well. So again, as I said in the previous class, like when we taught this, you don't really need to fully understand quantum mechanics. You can kind of understand it in the terms of, okay, SL plus half or minus half is the two states possible. But it's a good idea that you should look into angular momentum addition at some point if you are interested in physics. And if you take any quantum mechanics textbook, it is there. I would suggest Griffiths for this particular thing. So you can see that you should try to at least memorize till 50, I would say, the sequence of states. Unfortunately, I don't have any quick hack to remember it. All I can say is that it is not exactly like how you have in atomic physics, because in atomic physics, for example, you don't have a 1p state, right? You only have 2p. Because L and N minus 1 are related, but here N can take any value independent of L. So please don't get confused there. And always the higher spin multiplicity term will be lower in energy when compared to the higher lower spin. So you see 1p 3 halves is less energetic when compared to 1p half. And as per the off-Bohr principle, I think it's the off-Bohr principle, right? In atomic shells, when you fill them from the lowest energy to the highest energy, you have to do the same kind of thing here. So the way to find out how many what is a multiplicity of a state is basically to multiply this j factor as 2j plus 1. So you can see that this state, for example, 2 into 3 halves plus 1 is 4. That's why we can accommodate 4 nucleons here. And as I said to you in the class, the Pauli exclusion principle tells us that only 4 nucleons can go, but it can be 4 neutrons and 4 protons also. So it, for Pauli exclusion principle, only applies to identical fermions. So we can have proton and neutron of same quantum number in the same state. That is not an issue, so don't get confused there. So yeah, this is about the shell model and liquid drop model. And yeah, I think we did a few problems in this, so please try, you can, so I think 50 corresponds to calcium or something, so you can try. Is 50 calcium? Okay, I don't, yeah, I think 50 might be because 20. Yeah, you can, I don't remember exactly what particle has 50, but you can try to, I think 50 is not calcium. Calcium should be, calcium is 40, but 20 protons and 20 neutrons. Yeah. So 50 is something else. You can try to, yeah, okay, 50 is 10. Thanks. I'm very bad at remembering these things, but yeah, you can try taking up some particle up to 10, pick up zinc or something and try to do, the shell model up to that, for that particle, and see and look up what is the spin parity of the nucleus. So that is one of the things that is very useful about the shell model, is that it is not an empirical model. It helps us to actually predict the spin and parity of the element, which is of the nucleus which we are considering. So, choose an element at random, choose zinc or, iron or copper or something, try to solve for this. And as I told you, as in atoms, it is a valence nucleons that play a role, right? It is not the truly filled shells, it's the outer shells which play a role. So try to look at what should be the spin parity, and this is a very powerful model. Those kinds of predictions have been vetted by experiments. So I think that will be a good idea for your exam point of view to practice. You can just pick up any element at random and try to find its spin parity. And you can find out how the spin parity varies for different isotopes also. So like, oxygen 16 will have different parity when compared to oxygen 17, because the atomic number is different. So the number of nucleons and proton nucleons is different. So, okay. Yeah, so week 6, you looked at even more nuclear reactions. So till now, we have only looked at hydrogen burning, but you know that there are burning processes possible in stars all the way up to iron, as or second class. So here we were looking at the higher order processes. So triple alpha process is of course how carbon is formed, and triple alpha process actually has a very interesting discovery, because it was Fred Hoyle who invoked the anthropic principle to say how helium could burn to carbon, because uh, helium, it seemed like triple alpha was a very ineffectual process, but we know that carbon is very abundant in the universe and it is the basis of all life. So Hoyle argued that based on the fact that I exist as a human being, that tells me that carbon should be very efficiently produced in the universe, which tells me that there should be something helping out the triple alpha process, maybe a resonance state, and that's what he proposed as a Hoyle state. So you've already seen that history and how the Hoyle state and his prediction, which some have called a very bold prediction, but nonetheless it came true later. People were actually able to measure the Hoyle state, which as you can see has a particular energy and spin and parity. And also, of course, there are burning does not stop there. Also, we know that carbon fuses to oxygen and then to silicon and so on till iron. So the higher order nucleosynthesis reactions are also very important. And of course, we know that from the very first picture, let me just go here, that the stars kind of only produce a very limited number of elements, only up to really iron. So how do all the exotic particles beyond that come? They come because of supernovae and merging neutron stars and all kinds of exotic processes that are happening in the universe. In this connection, we looked at S and R processes, which are the slow and rapid neutron capture. And the platinum, which is, you wear in your rings, the very precious metals, it's actually very precious because it comes from these explosive events that happened all across the universe. So you can think of all those expensive metals in that way as well. But yeah, so this is, as I showed in that slide, big stars are like ogres because they have many, many layers. That when, as we saw in our stellar evolution lecture also, when one phase of burning ends, it ends in the core, it might still have a shell burning, what it's called. So, once ion is formed, the problem is that it's not an exothermic, it's an endothermic reaction, and it triggers a runaway kind of core collapse, which results in supernova. So we discussed this. I also showed you a video of how the simulation of that happens. And as I said, to create heavy elements, we kind of have these two reactions, the S process and the R process, either the slow capture or the rapid capture. The slow capture happens in the late evolutionary stage, where exactly this kind of picture, sorry, this kind of picture has come in, and in the outer layers, this is what is happening. So there is a, this is usually the slow neutron capture happens when there is not a lot of free neutrons around. So you need to capture neutrons slowly, and then whenever you capture a neutron, essentially you go to some sort of unstable configure isotope, because just capturing a neutron does not change the element, right? Protons only change the element. An unstable neutron always decays to a proton, or you can call that is what is called beta decay. And when it beta decays in in that way, then we move up because we get an extra proton, so we move up in the atomic in the periodic table essentially. So this is kind of what happens, and you can see that it takes place over many, many years, and over millions of years you get these kinds of elements. But of course, our process happens when you have a lot of free neutrons available. And I think I showed you a video about this. The best candidate for our process is kind of neutron star mergers, and you can see how fast it happens. So basically what happens is, because you have a huge number of free neutrons, the atom captures all of them, it becomes highly radioactive, and it beta decays and forms a much higher atomic number element when compared to the slow process. So the slow process can move you up, like if you think of it like a ladder, it moves you up one step at a time, whereas a rapid process is where you make a huge jump to some very big, to the very top of the ladder, and then you come down a step. So you're still like very much higher up in the periodic table if you think of it as a ladder. And that that is kind of how we picture nuclei and nuclear stability, because I showed you that there is this idea of the island of stability, which is this line of where the nuclei are stable and where they aren't. So you can think of slow process and our process as moving up the island of stability. Sorry, it's not called island of stability is just that part at the top. Generally, the line of stability is just a way of moving up the line of stability. The rapid neutron capture, the R process helps you to move, skip steps and move like far ahead, whereas the S process moves you up a step at a time. And this is the elemental abundance curve, which you saw somewhere here. So this is basically this picture. If you take this picture and then you also take this picture and you combine them together, then you will find this very nice picture. So one sec, let me just go to the relevant slide. So this very nice picture comes out. So you can see how this is tells you both the elemental abundance and the way that uh, they are produced. So you can see that, again, up to ion is only where we can produce through stars. Then through supernovae, you can produce a few of the higher elements. But really, for all these extra processes, you need S process and R process, where to produce all the heavy elements. And you can see that R process dominates in some elements, S process dominates in some other elements. So you can see that gold and platinum, for example, are very much from the R process. So maybe that's why they are so expensive, is because they literally come from two neutron stars explosively merging. I don't know if that is why they are expensive, but that is definitely why they are rare. Okay, so finally, in the last part of the course, now you have seen astrophysics, you have seen nuclear physics theory, you have seen how to marry them together and look at them together. So now for the last part of the course, you kind of came back to earth and you were seeing how to talk about how exactly these processes are measured. So this is where we talk about charged particles, neutron beams, accelerators, detectors, all those kinds of stuff. And you looked at particularly different kinds of accelerators. So this is like some nice images that I found online. So this is, for example, the synchrotron, which we spoke about in the class. Like these are relativistic cyclotrons, and they are needed to, because when we deal with materials that are extremely relativistic, we also spoke about relativity in day before yesterday's class. Like the LHC, for example, the Large Hadron Collider in CERN, which is where they actually discovered the Higgs boson, is has two protons which are moving at extremely high velocities towards each other, and these high energies are so high that they may produce new kind of exotic particles. So you can see that the LHC accelerates protons to 6.5 tera electron volts. So tera is like extremely high, 10 power 12, which is the highest energy in the world at present. You can see that how exactly it is set up. And similarly, you have cyclotrons. Cyclotrons, each of these accelerators have their own kind of thing. So you can see that cyclotrons are basically the non-relativistic version where it goes up to a few MeV, and they're used for medical research. And again, the whole reason for building particle accelerators, why are particle accelerators interesting, is when you because of Einstein's principle of relativity, which says that energy is just mass in a different form. So when we are able to push things to very high energies, that's also like pushing them to higher masses, right? So that's why, when you push something to a very high energy, then you're also able to produce certain medical isotopes which you might not be able to at lower energies. So you can see how exactly this is done. We have already spoke about how the magnetic field is configured in such a way that the particle just keeps going around and around, so that it keeps getting accelerated, as opposed to finally the linac, which is straight and to the point, as they say. So you can see that the longest linac is 2 miles long, and you can see how these are used for, again, to create beams of radiation for medical kind of purposes. So here you just have a straight path. So why we moved from this to the circular things, we have also discussed in the class. Because if I want to accelerate something in a linear way, I have to just keep on making my arms longer. Whereas a circular one, I can just keep going around and around until I get the energy that I want. So each of them have their own energy ranges, they have their own applications. And again, understanding the reactions that happen in these are very important, because that's how we can understand more about the fundamental nuclear physics, especially from something like the LHC. And then we can kind of figure out what's happening in more exotic systems in the world, sorry, in the universe, like for example neutron stars. And I think I told you, like, this is something that I work on personally as well, is that we still don't really understand what happens inside a neutron star. So the hope is that, as we move to more and more sophisticated experiments, we can understand some baseline things which we can then explore, kind of apply to more exotic systems. So yeah, finally in week 8, you ended with looking at more of these kinds of things, and especially the exact physics behind the collisions and the kinematics of it all. And in this class, I kind of took the liberty to introduce some special relativity to you, and how, approaching the speed of light causes changes in all of these different elements, and that makes us actually have to explore all different relationships from Newtonian physics. So as I said, quantum mechanics is non-intuitive to us because we don't deal with the length scales and mass scales where the wave nature is important. Similarly, special relativity is non-intuitive to us because we don't deal with velocities that are close to light. But where both those effects play a role is nuclear physics, because we deal with very small elements which are sometimes accelerated to very high energies and very high velocities. So it is important for us to understand. And we also saw how the exact collisions can be understood in different frames, which is a very, people talk about special relativity in the sense that it is the cosmic speed limit, but an important component of special relativity is also this freedom of choosing the frame, which is where we look at different sorts of frames of references, and the physics is equivalent in all the frames. So yeah, so that is your course from week 1 to week 8. So I have tried to like kind of give you a recap of the entire course, and I think you will appreciate my statement at the beginning, which is that over the 8 weeks that you have taken this course, you have actually covered a very large number of topics, and a very diverse set of topics, I would say. So I would say that, again, getting exposure to the topics is good. And I would say that if any of these topics catches your eye, please try to go deeper into the topic. Every topic is like a drop in an ocean. You can always go as deep as you want. So I encourage all of you to use this course as a starting point, so that you can take the exposure that you got from this course and apply it in your own fields of research, if you are in a research field. And I hope that at least some of you will continue on with astrophysics. So yeah, before I just have few more things. So one thing is that because your exam is coming forward, as I said, don't think of this course solely from exam perspective. Exam will come and go, but try to hold on to the concepts beyond just the exam. That will be a very good application of this course. But yeah, particularly for your exam and from problem solving point of view, I would say one is to try and connect things. As I said, can be very intimidating, especially when you have a course like this where there is a diverse set of topics, that there might be formulae which you feel like are all on different kinds of ends. But as I said, there is a clear narrative and kind of connectedness between the topics. So try to relate things to each other, so that especially those things like gamma peak, gamma energy, resonant reactions, those are very closely related. Try to study them together rather than in isolation. So another thing is that this is a general physics rule, is that dimensional analysis is your friend. So suppose you writing down a formula in the exam and you feel like you don't remember it correctly, or if you doubt it, the first check is to of course make sure it is dimensionally consistent, which means that make sure the units match up. That is a very basic thing. Of course, not every formula which is dimensionally correct is dimensionally consistent is a correct formula, but this is a very good way to first, at a first glance, have a check on your formula, right? So if you are doubting the dependence of t, for example, is it t power 5 or t power 6, you can always go and check which is consistent with your formula. So another thing is try to build intuition and check if your answers make sense. So that so in nuclear physics and in astrophysics, we deal with very diverse length scales, right? We deal with the length scales of atoms and nuclei, which are very small. We also deal with universe, which is very big, right? Light years and all that. So try to make sure that your answers kind of are matching the scales of the problem. For example, if you get a reaction cross section, that will not be in meters, right? It's not going to be a very big, that would be absurd. So try to do this. And of course, practice the problems. So as I said, I have included links in all the class sessions, and I would say that go see all those questions first. Make sure you know how to solve all the assignment problems and the past assignment problems which have been discussed in this problem solving class. Beyond that, check the links. I think most of the links do have problems in them. Beyond that, if you are having trouble to find some problems on some specific topic, please write to me. I'll try to help out as and when I can by this weekend. I guess the exam is next week. So in the next few days, if you write to me, I can help you. Don't write to me the night of the exam. That will be difficult. But yeah, if you write to me a little bit in advance, I can try to help you out, or at least point you in the correct direction. I think even before you write to me, just go online and search for lecture notes. Like what you'll find is a lot of universities, especially universities abroad, they make their lecture notes available. So just like how you have this NPTEL course, MIT, which is the Massachusetts Institute of Technology in the US, they have a very nice initiative called Open Courseware. So that's where they make their lectures, which are actually taught to their college students, available online. And they usually have assignments and problem sets available. So please go and search for MIT Open Courseware and search for like a nuclear physics or an astrophysics course. You will usually find that they have solution sets and problem sets. So you can kind of go and check those. You can try also problems from certain textbooks. I have included them here. And yeah, first and foremost, before all that, make sure you're clear with the exact problems done in the class by the professor, by the assignment problems, and these, with the, I think assignment problem solutions are already given to you. And also whatever problems have been done in these problem solving classes. Beyond that, I would say that first look at MIT courseware. That is a very good place to start. And also generally look for lecture notes. Like the lecture notes I have linked in my classes, they will have some sort of extra problem solving. I think there is some message in the chat. I can check it. Ma'am, any important questions? Okay, I think I guys told you guys already. I am an external TA. I have nothing to do with exam. I also do not know what the question paper is like. But I would say that focus on your assignment problems, focus on your past assignment problems, which are the problems that have been solved in the class. Try to start with those first, and then you can kind of move forward. So that you can see that even in the assignments and in the past assignments, there are some concepts which come up again and again. So it will be good for you to focus on them. I would say that, there are not many questions, right? In the sense that there is like maybe 10 questions per week. And of those 10 questions, per week, there are only maybe half of them are really problems, right? Most of them are theory based. So try to do those problems sincerely, do the assignment problems, do these problems, and check for lectures for the additional things. I think MIT is a good place to start. Other than that, if you search online also, it is very easy to find. So whenever I make these slides, for example, I usually search for the concept online. I try to find lecture notes from 2 3 universities. Don't use any old site. I would say use like some lecture notes from particularly a university, or better yet, use textbooks, use some verified sources. When you search for a problem online, you should also know how to discriminate between a good source and a bad source. Okay, so don't just follow any old source that you see. But yeah, usually lecture notes from universities, they are very good bit, and I have made such lecture notes which has helped me already available, so please check for those. And yeah, this is about the problem solving. So finally, before we end, I wanted to kind of give you guys a cheat sheet. By cheat sheet, of course, I don't think you can carry these formulae to your exam hall, but this will be like a good way. I'm just consolidated all the formulae, different formulae we have used in all our different problem solving classes, so that you have a place where you can quickly go and glance at some formulae. I have, to the best of my ability, collected all the formula, but I might have missed one or two. So if I have, you can just add it yourself. But yeah, this is basically for your convenience. So we'll just end with like looking at all the formulae once more and seeing if we remember all of them. So first of all, you have your basic physical constants and conversions. You have your speed of light, Planck's constant, Avogadro's number, and Boltzmann constant. I think you guys all know this, but for completeness, I have included it as well. Of course, these are the units which come up again and again. Fermi or femtometer is 10 power minus 15 meters. Fermi literally means in meters, of course. Giga, if the prefix giga comes, like gigakelvin, that's 10 power 9. Mega is 10 power 6. And 1 electron volt is 1.6 10 power minus 19 joules. And 1 barn, which is the measurement of area which is used in cross section, is 10 power minus 28 meters square. So these are all the kind of uh, constants and conversions that you come across again and again in your course. Then you have astrophysical sort of formulae that you used. So we, as I mentioned in the recap, and also I think in the very first lecture, stars are usually modeled as black bodies. So we can apply the black body physics in the terms of the Wien's law and the Stephen Boltzmann law. Okay, once. So if a question has T6 is equal to 20 Kelvin, then the temperature is 2 megakelvin. No, the temperature is 20 megakelvin, right? Because megakelvin means 10 power 6 and T6 means whatever value you have into 10 power 6. So it will be 20 megakelvin. Does that make sense? Okay. So whenever you see, yeah, so I should have noticed that T6, for example, means whatever number times 10 power 6. Similarly, T9 means whatever number times 10 power 9. So just multiplying. Whereas if I write 20 MeV, that means 20 into 10 to the power of 6 electron volt. Okay, so just be careful of that. So MK means 10 power 6 Kelvin, but T6 means also 10 power 6. So writing 6 in denominator and writing M are the same thing. Okay, cool. So yeah, be very careful. These are the small things. The reason I included that is because these are the small things where we make mistakes, right? You might know the formula very well, but you might mess up in this powers, and then you will lose marks unnecessarily. So I didn't want that to happen. That's why I included this. So thanks for asking, but I hope it's clear now. So yeah, astrophysically we have used some of these concepts have come up in your lectures. So as I said, we can approximate stars to be black bodies. So because of that, we can use this Wien's law and the Stephen Boltzmann law. The Wien's law tells you how to relate the temperature to the maximum velocity where, or the velocity peak of the distribution. Again, this is a distribution function when it comes to the Planck's law. So this is how exactly you can estimate the temperature of the sun by sitting here, because the sun's radiation is peaked at yellow color. So from that, if you do a rough calculation, you will find that the temperature of the sun comes to around 6000 Kelvin, which is also what the value you get from more rigorous calculation also. And Stephen Boltzmann law tells you the power or the luminosity which is emitted from a body. You can see that it is dependent on the area, which is basically r squared for a star, uh, and T, which is the temperature. Sorry, is there a question? Is there a question? I think someone unmuted by mistake. I'm just going to mute you. If you have a question, please ask now. Okay, I think it's by mistake. I'm muting you. If you have a question, you can unmute and ask, just because the background noise will cause interference. But yeah, so the other thing that came in the very early lecture was about the resolving power of telescope, which is based on the diffraction condition. I think you all know this. It is based on basically, what's it called? Rayleigh's criterion, 1.22 lambda by d. Then you have the yeah, this basically tells you how close two objects can be that can be resolved by a telescope. So, the smaller the resolving power is, the better the telescope is. Hubble's law is basically the law that dictates that the universe is expanding, and you know that it is expanding at a rate which is determined by the Hubble constant, and that has this value 70 kilometer per second by megaparsec. So, one sec, sorry, this D should not be here. Yeah, so yeah, it's a 70 kilometer per second per megaparsec, which basically tells you that for a galaxy that is 1 megaparsec away from us is moving at a velocity of 70 kilometer per second from us. So a parsec is kind of like a measurement of distance. It is around 3.26 light years, I think. Yeah. So it's like 3.26 light years. So a galaxy which is like basically 3 million light years away, that is moving at a speed of 70 kilometer per second from us. So the universe is accelerated and expanding, and that is Hubble's law. And also the Doppler effect is used when to measure, kind of estimate the distances from objects, because, and also, to define something called the redshift. So here Z is basically what's called redshift. And you know that when something is moving away from us, and this is something we experience on Earth also, when something is moving away from us, the waves which it emits undergo a change in frequency or a change in wavelength, and that is measured by the Doppler effect. So when a galaxy or a star which is moving away from us emits some light, then that light, when it finally reaches us, its frequency changes because of the motion of that planet, and that is what is called the Doppler shift, and sometimes it's called red shift, because as elements, or sorry, as stars or galaxies, as astrophysical objects move away from us, their wavelength of their light gets longer. So red light has longer wavelength, which tells you that the light gets red shifted. So this is all the astrophysical things that we used. Again, since this is a nuclear astrophysics course, these were kind of, there are not many astrophysical concepts to remember. This is basically black body radiation. This is your Hubble effect, and this is your resolving power, which I think you already know. Moving to before we move to nuclear physics, of course, we saw about Maxwell-Boltzmann distribution. So I'm repeating this picture because it has everything that you need. This is a distribution function. And as I told you, the Maxwell-Boltzmann distribution literally tells you that for a particle V in a distribution of molecules, how many of distribution of molecules at a temperature T of an ideal gas, how many of those particles, or what percentage of those particles have that velocity V. So this is a probability function, in the sense that when I plug in a velocity, I get back what is the probability of that velocity happening in my distribution. And if you minimize this, sorry, not minimize, maximize this by taking the derivative and putting to 0, you can get the most probable velocity. The mean velocity is got by, sorry, integrating this over all the velocities in the distribution, and the RMS velocity is got by getting the average squared velocity for the distribution and taking the square root. So this is basically the Maxwell-Boltzmann physics that you saw. Then you have the nuclear physics. So you had all the basic nuclear physics which you should know from even before the course. So you know that the radius of an atomic nucleus is directly related to the atomic number, or the mass not the atomic number, sorry, the mass number of the particular species, to the power of 1/3, scaled by some sort of constant, which is usually 1.2 or 1.3 for me. So if they don't give it to you, you can take it as either of these values. I think 1.2 is the more commonly used one. I've seen 1.3 very rarely used, so 1.2 you can use. And yeah, you can basically tells you how you can find the radius when you are given an atomic number. So they might just tell you that an atom of deuteron, sorry, a nucleus, deuteron nucleus, or a neutron atom. They will not tell you the radius of the deuteron atom, because it's understood, right? You can just put in the atomic number, which is the sum of the neutrons and the protons, and then find the radius. So they can just tell you what species it is, and you should be able to find the radius yourself. So don't expect that the radius will be given to you, right? And you should be careful with the atomic number, because for example, hydrogen and neutron, they both are the same element, right? Both are H, but their atomic numbers are sorry, I keep saying atomic number, the mass number is different. A is the mass number. So the mass number of hydrogen is 1, but the mass number of neutron is 2, because it has a proton and a neutron. So you have to be careful with how you do that, because that is what matters. You know that the binding energy is basically E equals mc squared, and of course here I've written delta E equals delta m, because you have to finally calculate the mass defect. So when 4 hydrogen fuse to form a helium, the final mass is kind of little bit less than the initial mass, because the rest of it has been, because a part of that mass has been released as energy. So you have to find the mass of the products minus the mass of the reactants and scale by c squared. And you know that this is the conversion that you have to use. 1 AMU is 931 mega electron volt per c squared. The Coulomb barrier, which we spoke about at length, and why the whole reason we need quantum tunneling, is given by this formula. So you know that Z1 Z1 Z2 E squared by R. So here you have Z1 electrons in the first species, you have Z1 Z2, sorry, not electrons, protons, both are same. Z1 protons in the first species, Z2 protons in the other species. So when you multiply them, you get this part, and this is how you get. The number density is given by, for any species Y, it's given by rho times the Avogadro number times the mass. I think someone had asked some question about this. The mass fraction is to be multiplied. I mean, yeah, but if you don't have a this is a general relation, right? It does not apply for mass fraction. So suppose if you have a compound and there is only one species, then obviously it's there. So mass fraction applies because mass fraction basically tells you 70% of this element is like this. So then you have to multiply it, obviously. So if you need that to be explicitly written, yeah, x of y needs to be multiplied. But my point is that this is a general formula which applies even if you have a single species. So mass fraction is there if I have hydrogen and carbon and helium, right? But even if I just have hydrogen, I can still find the number density, because the mass fraction is essentially 1 in that case. So does that make sense? So this number density has nothing to do with mass fraction, right? Mass fraction, in the sense that you have to scale everything by the mass fraction, because that tells you the percentage of atoms that are there. So that's why. But if you can also think of it as an x of y, and if there's only one species, x of y is obviously 1, which makes it uh, uh, this formula. So I can write it as the more general formula in case. Okay, one sec. Yeah, so right. So if suppose you're dealing with a compound, like we dealt with, I think, boron carbide or something in one of the later lectures, there it does not make sense to talk about a mass fraction. It is a single. It is a single. Is there someone who has a question? Okay. So yeah, there when I was just saying, like if there is a single element, then single compound, it does not make sense to talk about mass fraction, but you can still apply this formula. And from there, because for each molecule of boron carbide, you have four atoms of, it's B4C. So four atoms of boron. So then you just multiply the number density by 4 to get the boron number density, and you get the carbon number density as such. So that's why this does not just apply to situations where you have mass fraction. This is basically a counting problem, right? We have done this in our chemistry classes as well. So reduced mass, which comes in your gamma peak formula, is given by M1 M2 by M1 plus M2. It's a way to kind of convert a two body problem into a one dimensional problem. And finally, the thermal energy, which is how you convert a temperature to an energy, is given by E is equal to kBT, and kB is of course the Boltzmann factor. Now, when it comes to reaction rates and cross sections, you have a whole bunch of formula, but as I said, everything is related. So try to learn it in that way, spirit. That will make it easier for you. So the classical cross section is given by pi r squared. As I said, it's just shooting a bullet at a target. But of course, it's not as simple when you go to, the actual quantum regime and the actual reactions which are taking place. So you know that the reaction rate per particle is given by this kind of averaged over sigma v, and that gives you this integral, which you can, kind of motivate from your Maxwell-Boltzmann distribution and all that, because average of v is given by the Maxwell-Boltzmann distribution. And here, you know that this is a reaction rate per particle. So if I want to find it for the whole species, then I have to multiply by the number density, which is given here, right? And then the mean lifetime of the reaction is given by the total sort of reaction rate, and then taking the inverse of it. So this is the reaction rate per particle, which is here, and this is to apply to all the particles which are present in that species by calculating the number density. And finally, we take the inverse so that we can find the lifetime. So tunneling probability is given by this exponential, where this is the form of the 2 pi eta. This comes from your quantum physics, and we have discussed this both in the lectures and in the problem solving session. The relation between reaction cross section and S factor is given in this form, and again 2 pi eta is this particular thing. So whenever these units are written, it's very important that you have to use the values only in this units. So if you substitute E in mega electron volt here, your answer will be wrong, because this particular number 31.29 only comes when you substitute all the values in these particular units. Okay, so if you're substituting mega electron volt, this 31.29 has to be changed by root over 10 power 3, right? Because there's a 10 root over 10 power 3 difference. So be very careful, and especially in these formulae of gamma peak and width of gamma peak, these have to be in their specific. So if it's T6, it has to be without the mega Kelvin factor. So if it's T6, it has to be, if it's 20 mega Kelvin, T6 is 20. You should not put 20 into 10 power 6. Then you'll get the wrong answer, because the scaling factor has been calculated based on that value. So that's why I'm saying be very careful. Whenever the units are mentioned, only substitute in those units. So relation between reaction cross section and S factor also comes from this kind of way. This is the energy and the width of the gamma peak. Again, we had discussed this in the class. So as I said, T6 means only substitute T6. Don't substitute the actual value. Like if they give you 20 kilokelvin, for example, then that is 0.2 into 10 power minus 3 Kelvin, right? It's 2 into 10 power minus 2 mega Kelvin. So you have to substitute that value. You should not substitute 20 here. Okay, so just be careful. Reaction rate for narrow resonances, this is sigma v. So as I showed you in, I think, the previous thing, it becomes a factor of this resonance, what is it called? Resonance, strength of the resonance or whatever it is, which is depending on the width and all that. So you can substitute directly from omega gamma. So this I had discussed today's class. And finally, in terms of the experimental nuclear physics, you saw that the frequency of a cyclotron can be described in terms of, the magnetic field and the mass of the particle and the charge of the particle. So again, be careful about how you substitute things. It's not only depending on the charge, but the mass. So the frequency of an electron and a proton will be different because the masses of electrons and protons are different. You also saw about Compton scattering and how the energy of a Compton scattered proton varies. So I'm just going to remove this equals to pi. I'm sorry. So this is a general formula. It applies for all kind of things. And then the angle between the solid angle and plane angle, which is what we used in, I think, day before yesterday's class, we had just discussed this, which is that omega is 2 pi into 1 minus cos theta. Omega is the solid angle, which you can think of as like the two-dimensional subtended angle, and cos theta is, of course, the plane angle or the half angle. Then relativistic energy relation, I had showed you a video of how to memorize this. And basically, think of it as the arms of a triangle. And the Lorentz factor is gamma is 1 over 1 minus v squared by c squared, which can also be written as beta squared, where beta is v by c. So when the Lorentz factor is small, that kind of tells you that the system is extremely relativistic, and we have to take care to use the actual relativistic energy relations instead of just the normal relations, because as I told you in one of the previous slides, as we approach the speed of light, all these quantities are affected. So this is your cheat sheet of all your formulae. So try to, of course, remember them. But if you want a quick way to revise, I think this is a useful thing that you can just go and look at these formulae. Additional references for nuclear theory, I would say Crane's textbook is very good, although it is a very extensive textbook. So you don't really need it for this course. But if you need if you have interest in the subject and would like to take that further, I would highly suggest it. For quantum mechanics, I think I've already done Griffiths and Zetley. Statistical mechanics, which is not really there in this course that much, but again, it's very much related to the topics that you're learning. These are the books that I suggest. And generally, David Tong's lecture notes are very good for all the various subjects. Sidney Khan has a problem book, which is good. And MIT OCW lectures you can find at all levels, from basic undergraduate to a little more advanced. So I would suggest going there. And as I said, these lectures are very good in the sense that they have their assignments and solution sets usually posted on the website. So try looking that up. I can also add astrophysics textbooks. I would say that use Arnab Rai Chowdhury's book, who is a faculty here at IIC. He has a book which is very nice, which is about the basic astrophysical processes and all that. So you can try looking at that. If you are broadly interested in astrophysics, that's a good uh, place to start. So I think with that, the revision session is over. So with that, I want to leave you with a quote by Lise Meitner. So Lise Meitner was actually the woman who discovered, partly was responsible for the discovery of nuclear fission, along with a man called Otto Hahn. But Lise, she was a Jewish woman at during World War II. And for this reason, Otto Hahn kind of did not put her name on the paper, because at that time it was kind of risky to associate yourself with Jews, especially liberal Jewish women like who Lise was. And eventually she did not get the recognition even from, the Nobel Committee, who only awarded her co-author. So I just thought that it's very fitting that we are at the end of this course, and she has a very nice quote about how science makes people reach selflessly for truth and objectivity. It teaches people to accept reality with wonder and admiration. I hope that this course has helped you to reach those goals and actually look at your reality with some wonder and admiration, because it tells you exactly how the process is happening inside stars and, you know, neutron stars and all these very fantastical prospects are finally giving you the gold that you wear in your earrings. They are giving you all the elements that you use all around you. So yeah, with that I end the course, I guess. Supernova 1987A is, a picture that is a very famous picture in astrophysics. But I think now with this course you can appreciate this picture more, you can appreciate the processes which are happening here. So thank you very much for joining for the past 8+1 classes, and all the best for your exam. As I said, exam will happen, it will get over by Monday, but try to hold on to this course and all its, sort of different things. And I think if any of these topics have caught your interest, please try to follow up and, do it. We always need more astrophysicists. I'm always happy to talk to you guys if you need any more advice. And, I don't know everything, but I can, point you in that direction at least. As one of your people are asking, you have all my information, so please reach out to me. And yeah, please let me know if this course was useful for you. Like, this is my first time teaching like an online class like this. So if it was a good experience for you, please let me know. It will be very nice for me. This is my email ID. As always, this video will be recorded and posted on YouTube, and also all the links will be made available to you. So yeah, I think we can end the course now. So yeah, thanks everyone, and I hope that this was useful for you. The course was very interesting and nice. Yeah. Yeah, I will be sharing this video and all the slides. This course is really interesting. The only problem I face is not knowing nuclear physics, but yeah, maybe I will study nuclear physics now. So yeah, that is a problem that I also faced. I am an astrophysicist by training, so especially the last few lectures, I also had to learn along with you. So for that, I am also very grateful that I got this opportunity to have this course so that I could also learn with you. Where will you share? So I will share where all the course. Okay, have you not been seeing the? Okay, so the course YouTube page, all the videos have been shared on YouTube and all the slides have been made available on Drive. If you're not able to find the links, please go to this link in my website, and uh, you can find all the links there. So please go to this link in my website. Other than that, the nuclear, I'm saying NPTEL team should have made the links available to you. So if you're not able to find the links, just go to my website. Everything is available there. Any other course like this that we can join later? Yeah, I mean, NPTEL does a lot of interesting courses. I think you can keep a lookout. I think they have astrophysics courses. I know there's a fluid plasma course also in NPTEL, and fluid physics and plasma physics is another very interesting and very physically involved aspect of astronomy and astrophysics. So you can try that one. But yeah, other than that, I would say that even apart from NPTEL, as I said, there are lots of resources online. You can try the MIT Open Courseware lectures also. They are also very good. But yeah, already there is NPTEL course on. There is definitely a plasma and fluid course. I don't know about any other astrophysics courses off the top of my head. But yeah, they have such a huge list that, of course, I can't remember. Okay, so yeah, thanks, Vivek. uh, so I'm glad that, as I said, this was my first time teaching this course. I'm glad that it was a good suggest a good book for nuclear astrophysics for future. So I suggested books for nuclear physics and astrophysics separately. Nuclear astrophysics, there is some book, right? I forgot the Cradle Cosmos, some book like that. I forgot the exact name. One second, let me look. Cosmos of the Cradle or something like that. Yeah, Cradle of the Cosmos or some, yeah, from Cosmos to Cradle, some book like that. I forgot the exact name. But yeah, I would say that astrophysics and nuclear physics both, like, try to have your basics properly first. And especially, if you're going into nuclear astrophysics, you need to understand stellar evolution or whatever is the particular field you need. So that's one thing about astrophysics, is you need a lot of interdisciplinary kind of, maybe I can stop, interdisciplinary kind of thing. I think you would have had some books recommended to you from their courses. You can use those. Yeah, sorry, I don't do nuclear astrophysics. That's why I don't have textbooks off the top of my head. For compact star physics, if you ask me, I can give you. Cauldrons of Cosmos book is referred by professor is not available online. Can you provide us? Yeah, you should be able to find it online. I mean, even if I search, it will be online only. Okay, I will not condone this, but there are certain websites where you can search and find the books. I can provide you with the links after the class. You can try on LibGen if you can't find it. Or use your libraries. Usually in your libraries there will be books. So try to find, use your college library. I assume you're all in college. You should use your, it's not available. Oh, then I don't know. I also use LibGen for finding textbooks. Then I don't know from where I could get it. You can maybe write to the course instructor and ask him to provide it for you. But yeah, also use your libraries if you are near one. Always better to do that. Okay, I think, yeah, if you're not, it's fine. If you're not able to find a particular textbook, I would say that, go online. There are lots of lectures and lecture notes. You can try using them as well. And yeah, this course materials as well. Anyway, I think we can wind up the session now. If anyone doesn't have any more important questions, we can wind up. Thanks for your feedback. And yeah, I'm very happy to have taught this class because it helped, as I said, it helped me also to learn a lot of new things. And I hope that this course met whatever expectations you've had. Okay, cool. So let me stop sharing. Okay, bye everyone. Bye for the last time, and all the very best for your exam. Exam will come and go. Do it with a cool mind. Just remember, use the formulas and whatever that we have discussed. But yeah, try to at least follow up on some of the interesting concepts. If they have caught your attention, try to follow up and learn more about them as well. Yeah. Uh, sure. Okay. Bye, everyone. Bye.